Good morning, friends. In this lecture, we are going to study about the multiport S parameter. In the previous class, we have studied about what are the balance circuits, what are the advantage of the balance circuit. So, for the analysis of the balance circuit, we required a multiport S parameter. So, in the next slide, we first summarize what is a S parameter of a two-port network. Basically, at microwave frequency, input and output characteristics of a circuit can be represented in terms of S parameter. Basically, in the case of the S parameter, we represent input and output of a network in terms of the power. You see in the bottom of the slide, A1, A2, B1, B2 are incoming and outgoing waves at input and output of the network. Outgoing waves is basically a power because here the signal is propagating in the network. So we define voltage and in terms of incident voltage, current in terms of incident current. So and similarly output we have defined reflected voltage and reflected current. So a two-port network, voltages and current are defined in terms of incident voltage and reflected voltage, similarly incident current and reflected current. So in the next slide we see the S parameter of this two-port network. It is represented in terms of B1, B2 and A1, A2. And we know that the B1 and A1 are actually a power wave. That power can be represented in terms of the voltage. So see here AK, that is the power wave. K is the basically used as a constant that is having value 1 and 2 because it is a two-port network. So A is actually V plus divided by under root Z OK. Z is the characteristic impedance of this particular line. So here we see that power is converted in terms of incident voltage. Similarly B K, it is V K minus divided by under root Z naught K. Again here V K minus is the reflected voltage and Z OK is the characteristic impedance. So after substituting this value in the above matrix, we convert this matrix is converted in terms of incident voltage and reflected voltage. It means this particular matrix direct give the relationship of the S parameter to the incident and reflected voltage. But one thing you have remembered that in the case of the S parameter, we actually calculate the voltage powers and represent it in terms of the voltage. We are not measured the voltage, we measured power. So that is the difference between a S parameter and all other the two-port network. Similarly, in a two-port network, for example Z, Y, we have used for the analysis, we have used the short circuit and open circuit conditions. Here in the case of S parameter, input and output is not short circuited, it is terminated with a characteristic impedance. So that is all about the two-port network. I hope you are familiar with this type of network. In the case of the mixed mode S parameter, that is also called the balance network. See this the balance network. Here the two input terminal and two output terminal voltages is the incident is two voltages is defined VA1, VB1. Similarly, there are two current at input and two currents at output is defined. It means it is basically a four-port network. In the previous slide, we see a two-port network. So they have the only S11, S12, S21 and S22. But it is a four-port network. And for the analysis of this multi-port network, we use either the even mode and odd mode configuration. So in the case of odd mode configuration, that is called the differential mode, and even mode is called the common mode. So in the first, for analysis of this particular network, we mark a symmetry line in the network, and this symmetry line is virtually grounded in the case of differential mode, and it is a virtual open circuit in the case of the common mode. So For the analysis, we use the virtual ground in case of differential mode and virtual open circuit for the common mode. And when we have analyzed this network, we calculate the voltage and current in each case. It means in the differential mode and common mode both. We see this particular table. In the case of the differential mode, voltage is equal to VA minus VB, and representing the ports, because we defined at input or we defined at output. Similarly, in the case of the common mode, it is VA minus VB divided by 2. Same in the case of the current, situation will reverse. Differential mode, IA minus IB divided by 2, but in the case of the common mode, IA plus IB. Similarly, in the case of the impedances, we is represented by VD upon ID, where VD represent the voltage in the case of differential mode and ID represent current in case of differential. Similarly, VC and IC represent the common mode voltages and currents. So that is the basically method to analyze this multiport network. Then after this analysis, we write the S parameter of a multi-port network. So we already studied about in the case of the multi-port network, it is a 4-port network. So its S matrix is a 4 cross 4 matrix. This 4 cross 4 matrix is divided into 4 2 cross matrix. See these slides. Here the matrix is divided into 4 2 cross 2 matrix. But before analysis of this matrix, I first explain how we form this matrix. Here the basically S parameter can be obtained by considering all possible response over stimulus. Stimulus means the input. So the mixed mode S parameter can be written by considering port and the mode of the signal at that port. See there, the mode is the differential and mode is the common. And in the case of the differential mode, they have the 2 voltage. In the case of the common mode, they have the 2. Actually, for analysis point of the view, differential mode case, a pair of the signal applied at the input have opposite 180-degree phase difference. In the case of the common mode, the pair of the signal applied at the input having same phase. That is the difference between the differential mode and common mode for circuit point of view. But for the analysis of the circuit, we use a first we use the symmetry of the circuit, then divide our circuit, we draw a symmetric plane. Then this particular symmetric plane is virtual ground and virtual open. Virtual ground in the case of differential mode and virtually open circuit in the case of the common. So if we see that they have the 2-port differential case and they are 2-port the common cases, it means in the case of the S parameter of the mixed mode network, each element of the S matrix is actually represented mode and port both. So basically the first 2 column represent the differential mode, next 2 column represent the common mode. Similarly, see the matrix, first 2 row also represent the differential mode and next 2 row represent the common mode. Actually, we divide this matrix in row wise and column wise. So if we see in the column wise, first 2 column differential mode. If we see the row wise, first 2 row is again differential mode. So see this diagram. The first element is SD1 D1. D1 means port 1 in the differential mode configuration. Similarly, see the third element D1 C1. It means port 1 common mode configuration and similarly the port 1 in the differential mode configuration. So both. In that way we write we define each element of this matrix. Here one thing remember, in the case of the S parameter, first suffix always represent the output and the last suffix represent input. See the left hand side we have write S D1 D2. So the D2 is the input. Generally what we have follow nomenclature, we follow D1 is the input and D2 is the output, but here the nomenclature is reverse. So we have take care of these nomenclatures when we have write S matrix of any multi-port network. Not only in the case of the mixed mode, even in the two-port network, if there is S12, so the 2 is input, 1 is output. It means if we are write S21, it means it is a reverse traveling waves, that is called insertion loss also. And similarly S11 is the return loss, S12, S2, and both are called insertion loss. But if it is written S21, it means it is the forward traveling wave, and S12 is the reverse traveling wave. So please remember these nomenclatures. Then how this we have got a S matrix of a multi-port network, and we have studied about each element, what is represented, and then how we analyze this S matrix, and how we conclude by using this S matrix. So see this particular diagram. Actually this 4 cross 4 network is divided into 4 2 cross 2 matrix. So see the first 2 cross 2 matrix, all the terms represent D. It means this 2 cross 2 network basically show 2 cross 2 matrix basically show the performance in pure differential mode signal. Similarly, last 2 cross 2 network show the performance in case of pure common mode signal. It means if you analyze these 4 elements, we know the performance of a differential signal applied in the network, and last 4 elements show the performance of the network in the case of the common mode signal. Then again we move to the next slide. See this slide. Second 2 cross 2 network, it's describe conversion of the common mode signal into differential mode signal. So basically what is the common mode signal? It is actually the noise, because the noise if the noise attack on a particular electronic circuit, the phases are the same, so that is called the common mode signal. So it is the noise, and if this particular noise is converted into the differential mode, it means that noise will going to affect our the circuit. So what in the case of the perfect symmetry, this value is equal to the 0. This matrix, this 2 cross 2 matrix is equal to 0, and if it is the not the 0, it have the some value, because the most of the cases we have got asymmetric structure. So in the case of asymmetric structure, this value is not 0, so it represents susceptibility to EMI. EMI is electromagnetic interference. How it is susceptible? So that is the basically the parameter. Then we move to the third 2 cross 2 matrix. So it describes the conversion of differential mode into the common mode. It means our differential mode signal is converted into the noise. Differential mode converted into the common mode, it means it's converted into the noise. In the case of perfect symmetry, again its value is the 0. In the case of asymmetric network, it's not the 0. So it shows the basically electromagnetic interference, how our signal will going to two electronic circuit in the same place going to affect the performance. That is basically called electromagnetic interference. So basically in the definition point of the view, we define a CMMR, common mode rejection ratio. It is the basically a ratio of the differential mode gain to the common mode gain. We try to make the common mode rejection ratio infinite. It means high. Ideal case it is the infinite, so that we are able to avoid common mode signal. That is all about the mixed mode S parameter. And in the next class we have seen how we represent a mixed mode S parameter with the two-port network, because actual analysis we have a two-port network, so we analyze a two-port network and represent this two-port network into the four-port network. It means the mixed mode S parameter. So what are the different expression of SD1D1, SD1D2 that can be that will study in our next class. Thank you for your attention.